that one. Okay, yes.
Yeah, so I just wrote down a bunch of stuff that I know about this. And I guess maybe my question is I'm not really sure how to use it. So A and B are similar, and so A is similar to a symmetric positive matrix, right?
Yes.
So so we know that A has to have positive eigenvalues because we know that SOR converges for a symmetric positive definite matrix.
Yes.
But we're trying to show that it converges for A, which is similar to a symmetric positive definite matrix.
Yes.
So they both have the same eigenvalues.
Yes.
And is that what I mean to you?
Not quite.
Okay. So something else about the fact that, well, I mean, obviously, well, we know that D is diagonal too.
Yeah. So what? And that's going to turn out to be important. The thing is, because in this problem, you need to focus on the iteration matrix for SOR,
Oh, okay.
the M inverse N.
Okay.
And
What problem is this?
One.
One.
okay, can you hear me? Okay, I'm having trouble hearing you.
Oh, yeah, sorry, the volume.
Okay, I'm using someone else's computer. So, all right, now I can hear you better. All right, so we're just taking questions on the homework right now. Okay, yes, so the idea is, for B, you know that the iteration matrix that is obtained using like the D and the L and the U,
Mm-hmm.
that has its eigenvalues less than one absolute value because you know it converges.
Okay.
And you need to show that the same thing will happen for that iteration matrix for A.
Okay. But given what we know about A and B, then
Yes.
Okay. Okay.
And the thing is, when you have D, L, and U for B, how do they relate to D, L, and U for A? Yeah.
Okay.
So that's a key thing to check out, so that you can see how the two iteration matrices relate.
Okay.
Okay. That's a really weird look at the point. Not at all distracting. As is the pretending to pay attention look that you're giving right now. Other homework questions of any kind? On homework 2 or homework 3? Still waiting for some homework 2s. Not just you.
You didn't have to point it out that I had to bid, but okay.
Well, yes, because you gave me that look.
Yeah, but so.
Because I wasn't referring to you at the time. But
Oh.
you kind of invited it.
I have a question.
Yeah.
Is there any times Thursday or Fridays that it's okay if I was to come by or just set up an appointment with you through an email?
Let's see. On Thursday, well, not this Friday because I'm traveling, but Thursday, good time is like between 10:30 and 12:30 works.
Fine.
Okay. All right. Going once. Anything from a coast about a homework question?
No, not right now, not at this time.
Okay. At least, yeah, not yet, but okay. Okay, so now what does Skype saying now? Nothing. Or nothing bad. Okay. So, and you're already taping, so. Okay. All right, so now we can jump in. So actually in the notes, we're jumping back because we have a few more iterative methods discussed, and I needed to talk about these squares in order to do that, so that's why I'm jumping around a little bit into the notes. These are new notes. I added them like a week or 2 ago. So you make sure you have an up-to-date version of the notes. Alright, marker's alive for now, but we'll see how that goes. Okay, minimal residual, or minimum residual methods. Okay. All right. So first, a quick recap of certain properties of conjugate gradient. Okay, so the idea behind conjugate gradient is the solution after k iterations is has this form. It's a linear combination of vectors that are orthonormal, the columns of qk, so I can write them this way. Columns of qk, and they are orthonormal. And let's see, these vectors, they span what is called a Krylov subspace. And the description of that Krylov subspace starts out with a B, and then you keep multiplying by A until we have a k-dimensional subspace. Okay. All right. So the things of conjugate gradients, that method assumes that the matrix A is symmetric, positive, definite. Okay. Now, but the question we're going to look at now is, what do we have a more general matrix A that is still invertible but is not symmetric, positive, definite? So what we want to know is, can the same approach be used? Now, but right away, what we're going to find is that there are certain complications from just trying to seek a solution of this form for a general A and still have the same kind of efficiency. Because, actually, I think I'm starting to lose faith in this marker, but I have a fresh one in my office.